So, I don't know if you saw it. They scrubbed the Artemis 1 launch for August 29th. The next window is September 2nd. But in honor of Artemis, the rocket, the SLS rocket system with Orion launching on an uncrewed mission to the moon, kind of a big deal. I thought this would be a great opportunity to model something like that. Not the exact details, but the physics of a spaceship going from the Earth to the moon. So we're going to do it. I'm going to do everything you need to do to model this in Python. So I have no idea how long this is going to be. It could be short, it could be long. But let's go ahead and get started. Let me first say that this is kind of like what's called a three-body problem. Because and I'm talking about after it fires its rocket. So it's just free motion. We have the Earth, we have the moon, and we have the spaceship. And this is going to be the Orion spacecraft. At some point right here, the Earth pulls on the spacecraft, and so does the moon. So there's two forces acting on the spacecraft. But the Earth and the moon are also moving, because the Earth pulls on the moon, and the moon pulls on the Earth. Now, it's not really a three-body diagram would be the spacecraft pulling on those two things also, which it does. However, the mass of this is so small compared to these masses, it's not going to change their position. If it did, then it would be a three-body problem. So it's not a real three-body problem, but it kind of is. I mean, it kind of is, okay? But still, we're going to set this up and model it. And there's a whole bunch of things to visualize how to do this. So let's just get started with calculating the gravitational force. I already wrote down some stuff because I know we got a lot of things to do. So imagine that I have the Earth right here, and there's some vector location for the Earth, RE, and then I have the spacecraft over here, vector location RO. I can find the vector from the Earth to the spacecraft, vector R. It's just going to be RO, the final position, minus initial position, RE. And then I can calculate the gravitational force on the spacecraft from the Earth with this. So this says that the force on the spacecraft from Earth, EO, I'll put it like that, negative G, mass of the Earth, mass of the spacecraft, divided by the magnitude of R squared, and then I have to have this R hat, right? Because I want this back as a vector. I need it as a vector because I want to do the same thing for the moon, and I need to find the net force as a vector. So I have to add them as vectors. That's why this R hat, this is a unit vector in the direction of R, is important. Once I know the forces on the spacecraft, I can use the momentum principle. So this says that the net force is the change in momentum with respect to time. And if I pick a small non-zero time interval, then I can assume the net force is constant over that time interval. I think I'm going to pick something like delta t is 100 seconds, which seems long, but it's not that long in terms of the spacecraft's motion. If I assume that the momentum at the beginning of the time interval is p1, then the momentum at the end, based on this equation, is that initial momentum p1 plus the net force times delta t. So I can update the momentum if I assume the force is constant. And then, if I assume the momentum's constant, which I just changed it, which is kind of dumb, but it does work, then I can use the same thing to update the position of the spacecraft. And this just comes from the average velocity, the definition of velocity. And then I can just repeat this whole thing over and over again and model the motion of everything. That's what I'm going to do. Okay, so there's a lot of little parts. I'm going to jump back and forth between this paper and the computer, and I'm going to give you the code. But let's start off with the Earth-Moon system, because I can't model the motion of the spacecraft if I don't first have the Earth and the Moon. So here I have, and I'm going to do this in a cheating way, and that's probably not even to scale, but there's the Earth and the Moon. So I need to know the vector location of them. I can put this at the origin, but it doesn't matter. So I have our Earth. I missed. Sorry. Curved vector. Our moon. And we'll call this our Earth moon. The distance. Then I can do the same thing. I can calculate the gravitational force on the moon. It's going to be F Earth on moon, negative G. G is a constant. Mass of the Earth, mass of the moon, REM, squared r hat, rem hat. And then I can use that to update the position of the momentum of the moon. Okay. Now I do have to, I'm going to have a little trick here because I need to know if I just do that, and I can do the same thing for the Earth. It's the same force, just in the opposite direction. Okay. Now if I do that and I let this run, these things will just go crash, and they'll crash into each other. And I don't want that. I want the Earth, moon to orbit each other. But the moon does pull on the Earth, and the Earth does move. Now, there's a better way to model this. I'm going to do the cheap way because the moon doesn't actually orbit in a perfect circle, and I don't want to look up all the data, so I'm just going to build something that works. So let's say this. As if the moon was moving in a circle. I need to find this initial momentum, P moon 1. What's the initial momentum of the moon to make it move in a circular orbit? So let's call this REM. It's just a scalar, the radius between the Earth and the moon. And then I have a gravitational force pulling this way, and I can say at that instant, F net in the R direction, I'm writing this as a scalar, is going to be G, mass of the Earth, mass of the moon, over REM squared. And since it's moving in a circle, that's going to be equal to the mass of the moon times its acceleration, but it has circular acceleration. So the acceleration is towards the center of the circle, and it's going to be v squared over r. So let's say this is v, I'll put it as v0 squared over rem. And that's the radius of the circle, which is not actually true, but that's fine. That cancels with that, and I get v0, the initial velocity of the moon, is going to be the square root g, mass of the Earth, over the radius between the Earth and the moon. And so that will give a circular orbit. Now, like I said, that would work if the Earth was stationary, but it's not. I want to make the system stationary. So for the initial momentum of the moon, I'm going to use this. For the initial momentum of the Earth, I'm just going to use the opposite of the momentum of the moon. And that will mean the total momentum of the system 0. Okay. So let's go ahead and build an Earth-Moon system and get it to orbit, and then we'll add the spacecraft. Okay, so jumping over to Python. I already put some stuff in here, so I hope you don't think I'm like trying to cheat you or anything like that. Okay, so what I got here is the radius of the Earth in meters, the mass of the Earth in kilograms. This is that gravitational constant g, and then this is the radius of the moon, the mass of the moon, and this is the Earth-Moon distance. So I'm just going to make the Earth. That's all I'm going to do is make the Earth. Okay. So let's do this. Earth equals sphere. I'm in GlowScript v Python. Okay, so sphere is a reserved object, but that's awesome because we can make these three-dimensional objects. So let's put it at the origin, which I said don't do, but it's fine. So the position of that is going to be equal to vector 0, 0, 0. The radius of that sphere is RE. I'm just going to leave it right there. Okay, so let's just run that. Here's my Earth. Doesn't look like the Earth. We can fix that. So let's go over here and say texture equals textures dot Earth. That's a built-in texture in GlowScript v Python that makes it look like the Earth, and that's cool. Now, I want the moon to orbit around in this plane. This is the XY plane that we're looking at. And so we're looking at the Earth from the equator. I actually want to look at the Earth from the North Pole. So I'm actually going to rotate the Earth so I can do this. And don't worry about, that's not a big deal. Earth dot rotate. I need to give it an axis about which I want to rotate it. So I want to rotate about the x-axis. So axis equals vector 1, 0, 0. And then I need to give an angle. Angle equals, I think it's a pi over 2 or negative pi over 2. Let's say pi over 2. I can't remember which way it rotates. So let's see what happens now. So there. So now I've rotated it. So now we're looking at it from the North Pole. Okay. Yeah. That's the North Pole. Okay, so now I have the Earth. Now let's add the moon. So the moon is not the mon. The moon is a sphere. Okay, so the position, I'm going to put it on the x-axis. So I'm going to say position equals, let's just say earth.pos. I want to, even though it's at the origin, this will work in case I never need to move that. Plus REM times the vector 1, 0, 0. So I'll put it in the positive x direction. And then I'll say the radius is RM. And I'll leave it as white, even though it's not white. Let's just see what it looks like. Great. So I love this because it's like I can barely see the Earth. You can barely see the moon because they're tiny. Or the moon's tiny and far away. It's so far away. Let's just, I don't want to make it realistic. I want to make it cool. Okay, so let's go up here. And let's say, let's define this. Scale equals 3. I'm going to make both of them 3 times as big as they should be. So for the radius, I'm going to say scale times. Scale times. No, it's better. Okay. So all the textbooks do this. All the animations do this. No one represents this realistically because it looks terrible. So I'm going to do that too. I want to add a trail to the moon. So this means when it moves, it'll leave a trail. So make trail equals true. Okay. I think we're ready. I got the masses. I think I have everything. Oh, I need the initial velocity. So let's say V0. I already wrote this down. I'm just going to write it as square root. Oh, I need G. I got G. Square root G times the mass of the Earth divided by REM. That was it. And now I can give the moon an initial momentum. Moon.m. It's a lawnmower. Can you hear that? Moon.m. They don't know I'm recording, so I can't get angry. Right? Moon.m equals, no, moon.p equals the mass of the moon times vector. I want it to go in the positive y direction, so it's going to be 0, V0, 0. And then the Earth.p is just going to be negative moon.p. So whatever, now it's going to be going slower because the Earth has a much larger mass, right? Okay. It's okay to pause. Okay, t equals 0. dt equals 100. That's, I need a time step. Okay, so now let's do a loop. So while t less than, I'm going to say 10,000. Rate 100. I don't know about that rate, but that's fine. So I obviously want to let it run for a significant amount of time so I can see the motion. The rate says don't do more than 100 calculations per second. 100 loops per second. And so I don't want to let this run out in real time because it'd take a month for the moon to orbit. Now no one's got time for that. Okay, that's fine. So the first thing I'm going to do is to calculate the vector from the Earth to the moon. So I'm going to say REM, lowercase, which is dumb. I get it. Okay, that's a vector, and I'm using lowercase, and I have the scalar values to uppercase. This one's going to change, though. It's going to be the moon.pos, which is the vector location of the moon, minus Earth.pos, which is the vector location of the Earth. Okay, those are RM and R Earth. Now I can calculate the force on the moon due to the Earth. FEM equals negative G times mass of the moon times mass of the Earth times norm REM. So norm returns a unit vector. It's a built-in function in Python that returns a normal vector, a unit vector. Divided by mag REM squared. So mag returns the magnitude of the vector. So that's the gravitational force on the moon due to the Earth. Now I can use that to update both the momentum of the Earth and the moon. So moon.p equals moon.p plus FEM times dt. And now for the Earth, Earth.p equals Earth.p minus FEM times dt. So the force on the Earth is the opposite direction, so it has a negative value in there. Now I need to update their positions. So moon.pos, moon.pos plus moon.p times dt divided by moon, the mass of the moon, mm, and earth.pos. You could do the mass as a property of the object. You could say moon.m. I normally would do that, but I'm just trying to get these things done. Earth.pos plus earth.p times dt divided by mass of the earth. Now I need to update time. T equals t plus dt, and I think we're ready to run. I didn't even save it. Let's save it. Building Artemis model. I'll give you the code, like I said. Okay, let's run it and see what happens. Okay, so something is happening. Look, it is moving. So let's do this. Let's speed it up. Let's run this for a longer time. So that's 10 to the 5th. Let's do 10 to the 6th. 1e6. And let's do this at 500. So it looks like it's moving. So I think I'm pretty happy. Is the Earth moving? It should. I mean, it's kind of hard to see the Earth moving. We can plot it. I think it is moving, and I think I'm gonna be done with that. So overall, I'm happy. It looks good. Okay, moving in mostly a circular orbit. Yeah, it does look like the Earth is moving. I could plot the position of that or plot the momentum of the moon and the Earth, but I'm going to trust it. It's working out fine. So what I want to do now is to add in the gravitational force from both the moon and the Earth on the Orion spacecraft. So let's go back over to paper so we know exactly what we're doing, because we've got a lot of different variables going on here. Okay, so here's what we're going to do. So here's the Earth, and here's the moon, and then here's Artemis. Let's say it's right there. Okay, so I'm drawing my origin off to the side just so we know that these don't have to be at the origin. So that's, I'm going to call that RE. This is, oh, I got it right there. RM, the position of the moon, and this will be RO, the position of Orion. So I need to calculate two forces. I need to calculate the force due to the Earth, so I need this. I'll call this REO, Earth to Orion, and this will call RMO, Moon to Orion. So REO, it's going to be RO minus RE. That's an E. RMO is RO minus RM. And then I can calculate the two forces. So I can say the force of the Earth on Orion, FEO, is going to be negative G, mass of the Earth, mass of Orion. I'll have to pick that. REO hat over REO squared. And then the same thing for the moon. So then when I do the motion of Orion, I'm going to say F net is FEO plus FEM. Right? I have to have two forces on it. Now, the other thing I'm going to need to do is to say, well, where does it start and what is its momentum? So I'm going to start this at some initial, I'm going to start right below it, because that's what it looks like in the animations I've seen. I'm going to give it an initial velocity, VOO equals something. And I'm going to shoot it at an angle like this, at some angle theta. So the initial velocity vector, VOO vector, is going to be VOO times the vector cosine theta, sine theta, 0. And then I can update the momentum of that. Okay. So that's what I'm going to do. I'm going to pick like 3 Earth radiuses to start. I don't know the location. This is where, like, if you're a super space nerd, you can actually get this initial position and the initial momentum at some time. And again, no rockets here. This is after it fires its rocket. If you want to have a rocket thrust on it, you could say plus F thrust. You can add that in there, and then you can turn that off at some time. I'm not going to do that because I don't know enough about rockets. I know more about physics and Python. I don't even know a lot about Python, I'll be honest with you. Okay, so let me show you this initial velocity value. I did get that from somewhere, and I'm going to show you where I got that from, and then we'll program this in. So switching back to the computer, here, this is the Wikipedia page on Artemis. If you look at this animation, it gives you the initial speed right there. I paused it, and I got, let's see, I think I got 6 kilometers per second. 6 kilometers at the beginning. I'm going to use that, and we can change it. Okay. So let's go ahead and jump back to Python. I'm going to get out of that. So the first thing I need to do is to add Orion. So let's just call it Orion. Orion equals, I'm going to make it a sphere. You can make it you could build a cone and a cylinder and put little solar panels on it. That would be kind of fun, and I want to do that at some point. You can, and then merge those together in Python and make a 3D object. That's fun, but I'm not going to do that today. So the first thing I said is, let's just put the position as Earth.pos plus vector 0 -3 times RE, right? 3 Earth radii below. And I don't know why I picked that, just because looking at the picture, it kind of looks like that's something that would be realistic. Oh, and then 0. The radius, I want to make it visible. I don't want to make it the size of the Orion. So I'm just going to say radius equals the radius of the moon. Let's do scale times RM divided by 2. So half the radius of the moon. Let's make this one yellow because it'll show up better. Color equals color.yellow. And then make trail equals true. I need a mass. I feel like doing it this way. Orion.m equals 10 to the 4th. I don't know what the mass is. It doesn't really matter, right? Because that mass is actually going to factor out at the end. I do need, let's do this V0. You should never do that, but I just did. 6E3. That was the velocity that I start with. And then theta equals, let's say 10 degrees. 10 times pi divided by 180. So now I can get the initial momentum. Orion.p equals Orion.m times VO0 times vector cosine theta sine theta 0. Okay, I think we're ready. So down here, I need to calculate, I have the position of Orion. I need to calculate the force due to the Earth and the force due to the moon. So let's just first add this right here. REO equals Orion.pos minus Earth.pos. RMO equals Orion.pos minus Moon.pos. And then down here, I'm going to calculate 2 more forces. FEO equals -g times mass of the Earth times Orion.m times norm REO divided by mag REO squared. And then for the moon, FMO equals -g times mass of the moon times Orion.m times norm RMO mag RMO squared. Okay, so now let's just do it one step. Orion, now I'm going to update the momentum of Orion. Orion.P equals Orion.P plus FEO plus FMO times GT. So I have to add those two forces together. That's my net force on the Orion spacecraft. Now I can update the momentum. The position. Orion.POS equals Orion.POS plus Orion.P times GT divided by Orion.M. And that's it. Is that really it? Will that really work? Let's just see. Okay, so right here, that it looks like it's working, right? There's an orbit, and it's not completely circular because there is an interaction with the other moon. But I need to make it go a little bit faster. So let's say 6.2 and run it. Needs to go faster still. I can also maybe move it further away from the Earth, because if it's going further away from the Earth, the gravitational force is less. So let's just say 3.5. Okay, so it missed. It missed the moon, right? And so now it just escaped. So it's going actually too fast. So let's go with 3.1 for the distance. And I actually want to angle it below the x-axis. So let's make this theta as -10. Okay, nah, it's getting close. Let's see if it interacts with the moon. That was pretty good. Okay. I mean, so one of the things you have to be careful about is if the Orion gets too close to the moon, then your time step is actually going to be too large, and you can get this weird stuff. So I don't even know if that's legitimate. One thing I could do is to plot the total energy and see if the energy is conserved, but you got to be careful about that. The other thing is that remember that the actual Orion spacecraft is going to fire its lunar injection thrust maneuver. Okay, so it is going to slow down or do something to get into an orbit around the moon. And I didn't do that. I just launched it at some angle. But I got pretty lucky right there, and I'm pretty happy. So I think that is enough to get you started to play with this system. You can go in here. I'm going to give you the code, change the initial velocity and all that stuff, and see what happens. It's kind of fun. It's sort of like Kerbal Space Program, but you built it yourself. I've never played Kerbal Space Program, but I want to. So, okay. So hopefully that helps. Have fun. And I'll see you on the next Artemis launch. Hopefully it'll go off. That's it.